Ziegler-Neta polymerization. Polymerization by using Ziegler-Neta catalyst is known as Ziegler-Neta polymerization. So, Ziegler-Neta catalyst is an important discovery. It is an important discovery. And it is a special coordination catalyst. Ziegler-Neta catalyst comprises two components. One is a titanium metal part, or we can say a transition metal part, and the next one is an organo-aluminium part. Transition metal part is most commonly titanium chloride, TaCl4. Organo-aluminium part is most commonly R3Al. Actually, different types of Ziegler-Neta catalyst are there. Ziegler-Neta catalyst is usually formed by the combination of titanium Cl4 with any trialkyl aluminium. For example, if you react titanium chloride with triethyl aluminium, the Ziegler-Neta catalyst formed is TiCl4 Al Et thrice. So, Ziegler-Neta catalyst. And if we draw the structure of the Ziegler-Neta catalyst, for example, TiCl4 AlEt thrice, the structure will be like this: titanium containing 4 chlorine and 1 chlorine and Cl, and the next aluminium unit containing 3 ethyl groups, and the partial bond exists between these groups, titanium and ethyl group, and the same way aluminium and chlorine group. Then the structure of TiCl3 AlEt thrice will be like this: titanium, 2 Cl groups, then 1 Cl group here, aluminium, 3 Et groups are there, and partial bond between chlorine and aluminium, and in between titanium and ethyl group. So this is the structure of Ziegler-Neta catalyst. Here we are going to discuss the mechanism of Ziegler-Neta polymerization by using this one. So by using Ziegler-Neta catalyst, we can conduct polymerization reactions. Most commonly, this catalyst is used for the polymerization of olefins, that is double bonded compounds. So if we have a monomer unit like this, CH2 double bond CHR, if n such units are there, and by using Ziegler-Neta catalyst, we can prepare the linear chain polymer of this monomer, that is CH2 CHR n times. Then moving on to the mechanism of Ziegler-Neta polymerization. First step is initiation step. So in initiation step, our catalyst Cl, and the Cl, aluminium, Et, ethylene group, converts to a species like this, that is this bond shift here, and this will shift towards here, and we'll get species like this: titanium, Cl, Cl, and Et. One more chlorine is there. So plus we'll get Al, ethylene twice, Cl. So this is the species which initiate the polymerization reaction. So in the initiation step, this titanium species TiCl, Cl, Cl, and Et will react with an olefin molecule CH2, CH2, then react with alkene molecule. This form an alkene metal complex like this: titanium, Cl, 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 Et, and a complex and a alkene metal complex like this: CH2, CH2. Then the pair of electron from the carbon-carbon double bond will shift towards carbon-titanium bond. And the species will be formed like this: Cl, Cl, Cl. The partial bond between CH2, CH2. Bond between titanium and ethyl become weak, and a new partial bond will be formed between ethyl group and CH2 group. Here also the dotted line. Then in the next step, this bond entirely shift from here to here, and this partial bond to here, and we'll get titanium, Cl, 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 and here is a solid line, then CH2, CH2, Et. Then next olefin molecule is added into this polymerization reaction, or this process starts over and over and giving a linear polypropylene. So we can write the propagation step as the final product we'll get in the initiation step is this: titanium Cl3, CH2, CH2, Et. So when next olefin molecule added to this, what happens is, again this form a carbon metal complex. It is an organometal complex, an alkene metal complex like this: titanium, Cl3, and CH2, CH2, Et. This is the new alkene metal complex. And then the electrons within the carbon-carbon double bond is shift towards carbon-titanium bond. At the same time, this bond weakens and it shifted towards here, and we'll get this Cl, the partial bond CH2, single bond and a partial bond CH2, and a partial bond CH2, CH2, Et, partial bond between these two. So, this bond, and this becomes a solid bond CH2, CH2. Then this bond breaks, and this chain expanded as CH2, CH2, Et. This reaction will go on, and we can write it as titanium Cl3, CH2, CH2, CH2 CH2 N times ET. This is the species we'll get at the end of the propagation step. Then in termination, you can rewrite this molecule like this: titanium Cl, Cl, and CH2, CH, CH2, CH2 N times ET. Then the termination step, this bond shift to here and this carbon hydrogen bond shift here. So finally we'll get titanium Cl3H plus CH2 double bond CH, CH2 CH2 N times ET. So finally we got the polymer. This is the entire mechanism of Ziegler-Neta polymerization. Features of Ziegler-Neta polymerization. Most interesting feature of Ziegler-Neta polymerization is this reactions can be carried out in mild condition. So we can carry it out this reaction in mild conditions, such as in low pressure and room temperature, etc. Its stereochemical control is very high. Stereochemical control is very high. And hence we can prepare the desired polymer by using this reaction. The problem we always face during the polymerization reaction is if we want to prepare a linear chain, during the preparation we'll get some branch chain also. That is, we'll get a mixture of linear and branched polymers. But here in Ziegler-Neta polymerization, the advantage is that we'll get linear polymers. And the purity is 100%. That is, we'll get 100% linear polymer by using Ziegler-Neta polymerization reaction. For example, if you want to prepare polyisoprene units, this isoprene unit is this. This is the monomer of natural rubber, CH2 1,3-buta die, or isoprene units. So by using Ziegler-Neta polymerization, we'll get 100% pure linear polymer chain like this: CH2, CH, CH3, CH, double bond CH, CH2 N times. In normal case, we'll get a mixture of linear and branched polyisoprene units. But here in Ziegler-Neta polymerization, we'll get 100% linear polyisoprene units. So this is all about Ziegler-Neta polymerization.